quote from the Bee movie. I don't know if you guys have seen it, but it's a fun little movie. But at the beginning of the movie, they have this quote which says, there's no way that a bee should be able to fly because it's too fat and its wings are too small. But the bee flies anyway because bees don't care what humans think is impossible. Well, I'm going to show you that humans don't actually think that bee flight is impossible and tell you a little bit about why this theory has propagated. Okay, so my outline, I'll tell you a little bit about bee flight and some of the basics of fluid dynamics that are required to understand bee flight. I'll tell you then about the fixed wing model, which is the model that most people refer to when they say that bees can't fly. And then there's the flapping wing model, which is the more accurate model, which correctly predicts how a bee flies. And then I'll give you some conclusions. And this is a fly, not a bee. But it was the only picture I took that actually showed an insect well, so that's why it's included here. I didn't manage to get a good picture of a bee. Okay, so here's some information about bees. They can actually flap their wings at 250 hertz. This is higher than most other insects. Most other insects flap their wings at around 200 hertz. And an interesting fact about this is that 250 hertz is much faster than the bee can actually think. So each neuron signal that the bee sends to the muscles encodes many muscle movements, which allows for this quick speed of wing movement. Compared to other insects, bees have relatively shallow strokes. The stroke is basically just the amount of angle that the flapping takes. They're less than 130 degrees. Apparently, fruit flies can get up to 150 degrees. The wings are about 1 centimeter long. Bees fly at around 4 meters per second, and masses range from 0.05 grams to 0.6 grams. And these numbers will be a little bit useful later when I show you some sample calculations. Okay, so I'm sure a lot of you have learned about Bernoulli's principle in your introductory physics courses. Basically, here, if you have a fluid that moves, it requires a lower pressure, is the main thing I want you to get out of that. And I'll use that fact later on. Oh, and this is basically a restatement of conservation of energy for fluids. Okay, so the way that airplane flight and bird flight is modeled is based on this fixed wing model, which assumes that either the wing moves through a stationary fluid or a moving fluid moves around the stationary wing. Now, this seems like not a fair assumption because the bee wing is moving, it's flapping as well as moving through fluid. So it seems like there would be some more complications there. But we'll look at it to see if it correctly predicts how bees fly. And as you probably predicted the answer, it doesn't. So the way this happens is air flows differently above and below the wing. And above the wing, it creates a high velocity. The air around the upper part of the wing is at a high velocity. And from the equation I showed you earlier, this means that there's a low pressure. Some people will tell you that this is wrong, and Bernoulli's principle isn't applicable in this case because the density isn't constant. But the density doesn't change very much, so it's a pretty fair assumption. There's a lower pressure above the wing, and below the wing there's a higher pressure. So this causes a lift to be created. And this lift that is created is roughly proportional, this is very rough actually, to the length of the wing squared times the density of air times the velocity of the bee squared. And using the numbers I showed earlier, that's about 0.1 grams. In reality, this is actually probably an overestimate. The lift that could be created is less than 0.1 grams. And as I said earlier, bumblebees are only the smallest bumblebees are about that weight. So this doesn't seem like a good model to explain how bees actually fly. So there's this flapping wing model that gives a few predictions, predicts things differently. So what happens here is that the downward wing motion forms a vortex. Vortex is just a swirling fluid. So as you see here, the air around the wing is forming a swirl here, which is called a vortex in fluid terms. Again, the vortex is a moving fluid. So this vortex causes a low pressure, again, by Bernoulli's principle. And this low pressure causes the lift. And the faster the speed of this vortex, the faster the speed of the wing motion is, the bigger this vortex is going to be. And an interesting thing here, you see in this diagram that the vortex is not very closely attached to the wing here. The vortex actually stays with the wing about halfway, and then it leaves it a bit. And I'll talk about that a little bit more in a second. Okay. So there's a few stages to how the bee flies. Initially, there's the downward motion of the wing, which creates a vortex, like I said earlier. And in this initial stage, the vortex stays attached to the wing. So there's a large pressure difference there, so a lot of lift is generated. But in the second half of the wing going down, the wing has to decelerate. And in this process, the vortex leaves the wing a bit, and less lift is generated because the pressure difference isn't as great. But then, as the wing is about to come up, the wing rotates a bit so that as it's coming up, it'll again push the air in the same direction that it was before. So to actually enhance the original vortex that was there. And apparently the fancy fluid dynamics term for this is weight capture. So the bees have made this process more efficient. Instead of creating multiple vortices every time the wing goes up and down, they're actually enhancing the vortex that was already created when the wing was going down. And an interesting fact about what the bee will do if it's trying to speed up is it will increase the angle and not the frequency to speed up. As I said earlier, if you increase the velocity of the wing movement, it creates a bigger vortex, which creates a bigger pressure difference. And actually, it's more efficient for the bee to increase the frequency. But the bees will tend to increase the angle. And so this is, it seems weird that a bee would do this. And it actually hasn't been explained why this happens. Some people think it's because the bee just can't think fast enough to actually increase the frequency anymore because it's already kind of pushing the limits by going at such a high speed. Also, when bees are flying a lot, it usually means that they're collecting pollen and they have a lot of food, so they might just have a lot of energy and they don't really care about efficiency. But people are still studying that, which is interesting. And this process is, can sustain many times the weight of the bee. The equations associated with this type of motion are much more complicated than the simple equation I showed earlier. So it's kind of hard to predict how much lift it is. But through numerical models and stuff, it's been shown that this can sustain many more times the amount of weight than a fixed-wing flight can. So I'd like you to take away from this that bees can fly and still obey the laws of physics. There's no contradiction there. The fact why that theory is there is that fixed wing is a bad assumption because the wing continually moves. And these wing movements create vortices, which create pressure differences, which cause the lift of the bee. So thanks for listening.
Questions? So when you said about Bernoulli's principle, you said it's basically just conservation of energy. Can you go back and explain that a little bit more?
So if you divide through by the volume, the first is like a kinetic energy term, and the last term is a potential energy term, and the pressure is like a force. Yeah.
And you talked later about when it's not valid anymore, when the density variation is too much.
Right.
So can you say something else about what assumptions are here?
Right. So if we assume that velocity change causes a pressure change, it also could be that the density changes with the velocity, so the pressure doesn't need to change. But in most cases, in air at least, the density doesn't change very much. So that compensation is, yeah.
So if you assume roughly constant density, then you can convert something about pressure.
Right. Yeah. And I forgot to mention this, I guess, but Z doesn't change very much when bees' wings are flapping.
Any other questions? Everybody understood everything? Okay, good. Thank you.